project, our goal is to look into data about Detroit, specifically crime data and population data over various areas of Detroit organized by their zip codes. We are proposing this project for a variety of reasons, but it really does hit close to home for one team member in particular who's grown up in the Metro Detroit area and has worked in Detroit for multiple summers. Also, each person on our team has been to Detroit before due to its close proximity to Ann Arbor, and we thought it would be useful to pinpoint what areas in specific in Detroit are more so dangerous than others, in case any of us takes another trip to Detroit. Within our project, the specific question that we're trying to address is, what are the most and least dangerous areas of Detroit based on population and crime information? Detroit's safety rates are such an interesting subject because they have fluctuated so much in the recent years. According to the New York Times, around the 1950s, the expansion of the auto industry fueled a growth spurt that made Detroit the fourth largest city in the country. By 1950, the population peaked at almost 1.85 million people moved to Detroit to work at the big three auto companies, Ford, General Motors, and Chrysler. Yet despite this historical peak, Detroit has gone through a major economic and demographic decline in the recent decades, which can be attributed to 5 factors according to the New York Times. Those factors include reliance on a single industry, racial tensions, shortcomings of leadership, lack of an efficient transit system, and the impact of poverty. This decline has led to an increase in crime so sharp that Detroit's crime rate has placed it highest among cities with more than 100,000 residents. Now that we have tackled our team's motivation for this project, I will now talk about the data sets that we use for our project. Through the City of Detroit's Open Data Portal, our team was able to access our first data source, which included data about the different crimes that had taken place in Detroit. Each input in the database gave information regarding where the crime took place, what time it took place, and the type of crime that occurred. Our team accessed our second database through a website called Data Driven Detroit, which gave information regarding the population demographics, population size, and geographical area dimensions of certain zip codes in both Wayne and Oakland County. To use each of these databases, we downloaded them off of each website into a CSV file. We then re-uploaded and renamed those CSV files within our Jupyter notebook and read each comma-separated value file into a data frame. We also then converted the data frame into a SQL database, which we will explore later in the video. The variable which we thought was the most important was zip codes, as this was the variable that connected the two data frames together. We also thought that there were several other variables that were important in calculating which area was the most dangerous. In terms of the CSV containing crime information, we felt that the important variables included the type of crime that was committed, which was in the form of a string, as well as the date that the crime was committed, which was in the form of a date that could be converted into a date-time index. In terms of the population CSV, we felt that the important variables included the population density of each square mile of each zip code, which was in the form of a float, the total population of a zip code, which was an integer, the population under 18, which was an integer, and finally the population under 5, which was also an integer. We focused on crimes that took place between 2016 to 2021, as mentioned. However, when we first received the crime data frame, we decided to set the column labeled Incident Timestamp to a date-time index and sort it in ascending order. In doing this, we found that there were some crimes recorded from years outside of the date range we wanted to use. Specifically, the crime data could be dated back to 1915. Therefore, in order to gain a database that had all the information we wanted to collect, we sliced the database from 2016 onwards. In terms of the records that we retrieved, the original population database had a length of 174 entries, and the original crime database had a length of 348,247 entries. After merging the databases, the total length of the final database was 348,247. The reason for this is because all the entries in the crime database included a zip code that was inside of the population database. Now that we have tackled the motivation for our project as well as the data sources that we use, we are going to look at the data processing techniques that we used. After uploading our CSV files as pandas data frames, we needed to edit the column names to make them more comprehensive. In the total population data frame, we changed the column ZCTA5CE10 to the label zip code. This is to ensure not only that we understood what this column meant, but also this way we would have a common key in the total population data frame and crime incident data frame to merge on. When merging the data frames on zip code, we did not specify the type of merge, which defaults to an inner merge. We chose this option because it will keep the zip codes that are in common between both the total population and crime incidents data frames. Each of our team members did a separate analysis of this merged data frame in order to answer our overarching question. We are first going to start with Maya's analysis. After merging the data frame, Maya set the incident timestamp as a date timestamp and set that as the index of the data frame. Her analysis was aimed on finding how many crimes there were in each zip code compared to the total population of each zip code.
We started by making these two data frames grouped by zip code and year with the population and total number of crimes. Because they both have a multi-level index of zip code and year, we could merge them into one data frame, use an apply function to find the ratio of crimes to total population, and add that to a new column. From the data frame that we just created, we were able to create a pivot table. So in the rows, we have all of the different zip codes for Detroit, and in the columns, we have the years from 2016 on. For the values, we used the ratio of number of crimes per total population that we calculated previously. So from this pivot table, we were able to loop through the different rows and print out the zip code with the highest ratio of crime to population for each year. Here's a summary of the more dangerous zip codes in Detroit because they have higher numbers of crimes per the total population. For this next part, we converted the merged data frame to an SQL table called crime. Initially, we tried converting both data frames to SQL tables and doing an inner join. However, we were having issues with the column names and it wasn't recognizing column names that were in the table. To solve this, we merged the tables with pandas and converted it to SQL after. This table still included all of the random crime incidents, including the crimes from the early 1900s, so we created a new view of the table and called it Recent Crimes. This only included crime incidents from 2016 on. We were then interested in finding the most frequent crime for each year. To do this, we used a nested select statement to group the table by year and offense description, ordered it by year and the count of each offense, and returned the crime that occurred most for each year. According to this analysis, assault and battery, or simple assault, is the most common offense in Detroit.
My goal for helping to answer the question of what are the most dangerous areas in Detroit was to analyze how population density impacts crime rates. In other words, I wanted to understand if more population-dense areas were also more dangerous. In order to accomplish this goal, I first did some data processing in order to make the data easier to work with and obtain the results I was looking for. I first read in the data from both sources and then renamed the zip code column in the demographics data frame to make it neater. I then performed a merge on the two data frames on the zip codes column because the zip codes were the common factor between the two data frames I wanted to analyze the data on. I then created a new data frame called POP with just the zip code column, POP per square mile column, which is the population density, and year. This is because I am trying to find the zip codes with the highest crime rates per year based on population density, so I really only need these three columns in my analysis. After taking these steps, I was ready to start analyzing the data and find out if more dense areas have higher crime rates. The variables I was looking at in my analysis were primarily population density per square mile and yearly crime for each zip code. In order to do this, I first needed to find the average population density for all of the zip codes and the average yearly crime rate for all of the zip codes. This gave me a sort of baseline to compare my observations against. I first found the average population density for all of the zip codes by getting all of the unique population density values from the data frame I created, since the zip codes and the densities were repeated many times as each row represents a different instance of crime. I then summed these densities and divided by the number of densities to get the average. In order to get the average yearly crime rate, I first created a new data frame with just the zip code and year columns. I then performed a group by and got a count of total crimes by year and zip code. I then looped through all of the zip codes and computed the average yearly crime rate for each zip code and added this to a list. I then got a total average yearly crime rate for all of the zip codes by summing all of the averages in this list and dividing by the number of values. I then wanted to create a final data frame where I could aggregate all of the information I just gathered and make it more visually appealing. I first added three columns, one for all of the unique zip codes, one for the population density of each of these zip codes, and lastly, one for the average yearly crime rate for each of these zip codes. I then created two columns comparing each zip code's population density and average yearly crime rate to the total average population density and total average yearly crime rate that I just calculated. Essentially, any zip code with a population density above the average was labeled as high density, and any zip code with an average yearly crime rate above the total average was labeled as high crime, and vice versa. I then wanted to find what percentage of high crime areas were also high population density areas. To do this, I first found the number of high crime and high density areas and then the number of high crime areas and calculated the percentage. I found that roughly 77% of high crime areas were also high population density areas. This makes sense intuitively and goes along with the predictions we made at the start of this project. I then decided I wanted to create a scatter plot comparing population density on the x-axis to average crimes per year on the y-axis. As you can see here, there is a very strong positive correlation between population density and average yearly crime. Finally, I wanted to perform a t-test to confirm my results. I imported the Skippy stats module and used the t-test built-in function to compare the high population density crime rates and the low population density crime rates. The null hypothesis in this test is that high-density areas and low-density areas have no difference in average yearly crime. The alternate hypothesis is that high-density areas and low-density areas have different average yearly crime rates. I found that the p-value for this t-test is 0.00079, meaning that at a confidence level of 95%, the relationship between population density and crime rates is highly statistically significant, and we should reject the null hypothesis. Overall, this matches what we predicted and confirms our intuitions.
After merging the data frames together, I wanted to compare data about the number of crimes in each zip code to the zip code's population demographics. To do this, like Maya, I first set the column incident timestamps to a pandas date timestamp and set it as the index of the data frame, such that I could organize the crimes by the date that they occurred. I sliced the data frame to reflect only the crimes from the 1st of January in 2017 to the 31st of December in 2017. I decided to only focus on crimes from 2017 as I wanted to pick a specific year to analyze crimes for. I chose 2017 specifically because I didn't want to pick a year that the data started or ended on, as I felt like there would be a chance that some months might be omitted. Next, I used an apply function to group by each zip code and find the percentage of the population that was under 5 years old. I did this by using the values from the column population under 5 and dividing by the total population of each respective zip code, and then multiplying by 100 to reflect a percentage. Next, I created another data frame with this information, which ended up giving me a data frame which displayed all crimes under each zip code, as well as a column regarding the population percentage under 5 for that zip code. In order to find the number of crimes which were reported in each zip code for 2017, I used the group by function and aggregated the length of the number of entries per zip code and created a new data frame from that. Finally, I merged the data frames for population under 5 and the number of crimes in 2017 on the attribute zip code, and renamed the columns crimes in 2017 and population under 5. When I originally wanted to compare the population percentage under 5 to crime incidents, I realized that the scale for both of these variables would be quite different, as the number of crimes would be in the hundreds and the population percentages range from 0 to 35. Therefore, I decided to convert the number of crimes for each zip code into a percentage by dividing each crime occurrence by the total number of crimes for 2017 and multiplying that by the number 100. When initially looking at the data comparing zip codes' percentage of their population under 5 and crime occurrences in 2017, it was difficult to get an understanding for the relationships between these two variables. First, I sorted the visual from the lowest population percentage under 5 to the highest percentage. Through this, I discovered that these top 5 zip codes had young population demographics in comparisons to the others. Then I sorted the visual by the zip codes with the highest percentage crime and found that these were the leading zip codes in this domain. Through this brief comparison of these two lists, we can see that the zip code 48228 was in the top 5 for both population under 5 and high crime rates in 2017, making it both a dangerous place as well as a place that many children live. We did a similar analysis of the population under 18 versus the number of crimes in each zip code and found that 48224 was another zip code that was in the top 6 for both high crime and a high percentage of minors in its population. Additionally, the zip code 48205 is another zip code that falls in the top 6. Next, we will summarize our findings in answering the question of which areas of Detroit were the most dangerous. Through Sierra's analysis, we found that 48205, 48224, and 48228 all have high crime rates per population and have a very young population in comparison to the other zip codes. Out of all these zip codes, 48228 had the youngest population and highest crime rate, as it fell in the top 5 for both analysis done on population percent under 5 and under 18. A limitation of Sierra's analysis was that the size of each zip code was not taken into account when comparing the number of crimes. Maya's analysis, on the other hand, factored in each zip's area, and through her analysis we discovered that both 48243 and 48226 had the most crimes per population for 2 years each, making each of these zip codes high crime areas given their size. Through her SQL database, we found that the overarching most frequent crime was assault and battery. Through looking at the 5 dangerous zip codes proposed, assault and battery was the most frequent offense for all zip codes besides 48243, which was accident hit and run as the most frequent crime. Through Mary's analysis, we confirmed through statistical analysis that population density and crime rates are highly positively correlated. Some of the most dangerous area codes are also population dense, including 48228, 48219, and 48227. Given that 48228 was discovered as the most dangerous place from both Sierra and Mary's analysis, if we had to choose the most dangerous zip code, that would be the most dangerous location in Detroit. It would likely be this one.